Demand-side management program for mid-sized manufacturing organizations. Let's start at the home. You put a smart meter at the point of supply by Eskom and monitor hourly and daily usage. Then you identify and target high consumption points, e.g. lighting, swimming pool, geyser, air conditioning, and you make changes. You put a geyser timer, you put LED lights, you put a gas stove, you put a pool pump timer. You then monitor how the daily usage changes in the smart meter. Let's move to the factory complex. Again, you put a smart meter at the point of Eskom supply and monitor hourly and daily usage. Here, you identify the target high consumption units, e.g. office block, premix plant, packaging plant, engineering workshop, and laboratory building. You create various initiatives for each unit to reduce total energy consumption, and you coordinate various production managers to sequence operations to minimize the maximum power demand. Let's move to a hub of factory complexes in an industrial park. Here, again, you install a smart meter at the in-feed substation and monitor hourly and daily usage. Here, you identify and target high consumption factory complexes within the industrial park, e.g. the glass factory, the tire factory, the chemical processing factory, the agro processing factory. At this point, I'd like to introduce the spring hub of factory complexes. The hub has 130 factories, and top 6 factories in the hub consume 70% of the total energy supplied by the substation, and the 30% balance by the 124 remaining factories. This hub is supplied by the 60 MVA spring substation. You can approximate to 60 megawatts. This hub can be imagined as one giant factory, such that the energy saving, demand side management, demand peak clipping, standby power generation initiatives can be coordinated and managed at hub level. Therefore, a full substation can have energy reduction performance contract. They coordinate the energy reduction initiatives and maximum demand initiatives for their group of factories. E.g., for 8-hour shift operations, they all coordinate to split 33% work the first 8 hours, another 33% of the factory's work the second 8 hours, and the last 33% works the third 8 hours. This way, you will reduce the maximum power demand by 66%, but maintain the continuous energy consumption over the 24-hour period, rather than concentrated in an 8-hour period. Another example, if, for example, 70 factories only operate 5 days a week and stop Saturdays and Sundays for maintenance, these factories split themselves into 3 groups. Group 1 stops for maintenance Monday and Tuesday. Group 2 stops for maintenance Wednesday and Thursday. Group 3 stops for maintenance Friday and Saturday. In this example, there will be a 33% reduction in maximum power demand during the week, as 33% of the factories stop production for 2 days during the week to conduct plant maintenance, but will still have the same energy consumption. Both these options will cost the manufacturers more on labor costs, i.e. paying off shift allowances, weekend work, and overtime work. However, they will release substantial megawatts to the grid during peak demand period to benefit the economy and the country. The ideas discussed above for the hubs are simply load shifting or balancing options. There are also options for permanent load reduction opportunities, i.e. energy saving opportunities, including use of high efficiency electric motors, compressed air system energy optimization, conversion to energy-efficient flood lighting and indoor lighting based on presence or human presence detection, HVAC energy optimization programs. The third element is energy cogeneration by the hub, inverters and battery storage systems, gas generators, diesel generators, rooftop solar, and feeding of excess cogeneration energy back to the grid by the hub. And for these energy contributions by the factories, Eskom has developed programs to compensate the factories for this, both in financial terms, meaning Eskom pays the factories back for the effort, and secondly, guarantee of energy security for that hub, meaning that a substation hub that delivers the megawatt savings is exempted from load shedding, as they would have voluntarily curtailed energy proactively. Let's go back to the Spring hub. It is fed by a roughly 60 megawatt substation. If we are able to activate 100 industrial hubs across the country, we are talking 6,000 megawatts. At roughly 50% Eskom EAF, power station capacity required to service these hubs is 12,000 megawatts. Therefore, a 30% overall energy saving from these 100 hubs will equate to a full power station of 3,600 megawatts. Construction of this size power station is above 200 billion in capex costs and takes over 5 years. As of June 2023, we launched the Springs Hub pilot and extended the pilot to include Wadeville Hub and Spartan Hub in Ekurhuleni, Gauteng. We are looking to add 2 more in the pilot, in a different area and with direct Eskom distribution supply to add diversity to the pilot. This should help us develop a solid template from which we can onboard other industrial hubs in various provinces across the country. It is clear, therefore, that the biggest challenge is to get the hubs of independent factories to coordinate operational activities, centralize and optimize energy management at a hub level.